Multi-degree of freedom systems. By the end of this section, you're going to be able to find the equation of motion for multi-degree of freedom systems using, typically, Lagrange's equations. You're going to be able to find the multiple natural frequencies and multiple mode shapes of these multi-degree of freedom systems using the equations of motion in matrix form. You're going to be able to find the total solution to autonomous, conservative, multi-degree of freedom systems using principal coordinate analysis. And finally, you'll be able to find the steady state solution to forced multi-degree of freedom systems, specifically with simple harmonic forcing. So how do multi-degree of freedom systems differ from the previous section on 2-degree of freedom systems? Well, we're going to see that our analysis methods are very similar, but just more generalized versions of what we saw in 2-degree of freedom systems. And a multi-degree of freedom system is simply defined as having more than 2 degrees, but still a finite number of degrees of freedom to distinguish it with Unit 3, where we'll talk about continuous systems. So we're still going to use matrices, we're still going to use the eigensystem like we use for 2-degree of freedom systems. A multi-degree of freedom system is going to be used in Unit 3 to approximate continuous systems. As we expand on our analysis that we started with 2-degree of freedom systems, we're going to be creating a set of ordinary differential equations to solve, in contrast to what we're going to see in our continuous systems in Unit 3, where the exact solution is going to depend on a partial differential equation. And PDEs are typically much more difficult to solve than even a set of ODEs. So this becomes the basis of finite element analysis in Unit 3. Finding exact solutions as we keep going up in dimension is going to become more and more difficult, especially as the forcing functions could become more complex. So we're going to still limit our focus of forced multi-degree of freedom systems to the simple harmonic type of forcing that we saw in the previous section. But once again, for more complicated types of forcing, we could go to a numerical solution for now and employ something like ODE 4.5 and put everything into a state space form. So how do we see that we have a multi-degree of freedom system? Well, we're going to see that we have generically, we'll say n equations of motion, which we're going to derive typically using Lagrange's equations, but they could come from Newton's laws or other methods as well. And this will look very similar to what we saw for the 2-degree of freedom system. We want to put our n equations of motion into matrix form, where we're going to have a mass matrix, potentially a damping matrix, a stiffness matrix, and then the right-hand side could have a forcing function. But now, more generally, each of these matrices MCK is going to be n by n, where n is the number of independent degrees of freedom that we have, and our x vector is going to have n elements to it. So when we see that our equation of motion is in this form and we have an n degree of freedom system, well, the method for solving for all of those degrees of freedom analytically is going to depend on, one, is this autonomous or not? Do we have the zero vector on the right-hand side, or do we have some sort of forcing function? And it's also going to depend, is the C matrix the zero matrix, or do we have damping in our system? But the types of systems we're going to be looking at in this course are going to mirror what we saw for 2 degrees of freedom in what we're going to be able to solve for analytically.